Good evening, good evening, good evening. Year 12 and 13 chemistry students, welcome to your first of three lives this week, where we're going to be talking about the major topics from year 12 that come up in A-level exams. So don't worry, year 12s, we're focusing on year 12 stuff. That's it, just focusing on year 12 stuff. Yeah, please feel free to say hello in the chat. Let me know what your exam board is. I'm going to be covering all the major ones, okay? So AQA, OCR, Edexcel, and WJEC if you're in Wales as well. So I'll be covering everything I talk about in these three sessions this week is going to be in all of those different exam boards, because you know what, doesn't matter what exam board you are, chemistry is chemistry, and I can give you tweaks and things like that if we need them. So feel free as we go through to ask questions in the chat. Now, the point of this week, as I say, is twofold. One, it's like a revision session for you guys in year 12. I'm sure a lot of you have got internal exams coming up. Maybe not WJEC year 12 because you've done your exams. In fact, your Unit 2 exam was today. And I know all of you do that. But in England, not so many people sit AS exams anymore. It's more about internal exams and stuff like that. So what are we going to be doing over the course of this week? Well, we're going to be focusing, like I said, on those three topics that come up the most for year 13s in A-level, but of course it's going to be really, really helpful for you guys in year 12 as well. So just make sure, like I said, any questions as we go through, say hello in the chat and ask your question. Now, I'll be putting some links in the chat as well. Don't worry, they are perfectly safe links. They're to a Google Drive document that I'm going to be sharing with you guys. I got some question packs, I've got some cheat sheets for you as well today. And that, my friends, is where we are starting. Now, everything I do is exam focused. Yes, there are things you need to learn in A-level chemistry, but it's more about what you can do in A-level chemistry. So there, organic is one of those areas, and there aren't many of them where just repetition and learning and parrot fashion kind of like recall, if you like, comes into play. All right. The major areas are organic chemistry. The other ones are transition metals, okay, and the other ones, and tests for ions and stuff like that. And then, of course, there's a handful of definitions in there you need to know. So classic revision is less impactful on your grade than actually practicing questions and applying your skills in A-level chemistry. But you know what? Like I said, you got to learn those organic reactions, right? So here is something to help you. Now, I'm just going to move this out of the way. So these links I'm about to put in here, these are your reaction trackers, okay? So reaction trackers are basically the things you can use to help learn the different reactions, the different conditions, the names of the mechanisms, and so on and so forth, okay? So this first one here, this one is your AQA one, okay? So I'm just going to copy this here. I'm pretty sure this is the correct order, and you'll find out when you click on it. So that's your AQA one there. I'm just going to double check that is the correct one. No, that's OCR. So well done, Rich. So I must have kind of done these in the wrong order. So let's just kind of get rid of this. I do apologize, guys. Okay, I will put the OCR one back up. Okay, so is this the AQA one? Let's just check. I should have labeled these first, shouldn't I, really? No, that's not it either. There we go. That's the one. Okay, so this one here, this is your AQA one. Okay, so that's first up there. And this one here, this is OCR. Boom, there it is. And what's next? Let's do Edexcel next. So these are free for you to kind of download and use and abuse as you see fit. And then last but by no means least, because, I'm a proud Welshman, WJEC. Boom, there you go. So these are for you to download. Now, let me just show you exactly what these are and how to use them, okay? Because we're not going to sit here and just go through every single reaction. That's not how you learn, is it? It's spaced repetition. That's how you learn these things. So on the iPad here, this is the AQA one. I've not got all of them on here. This is the OCR one. So you can see these are 100% bespoke to your exam boards. If there's any slight differences in what the exam board expects in terms of answers as to the names of reactions or the conditions or anything like that, then you've got it on here, okay? So what you can see, if I just zoom in a little bit, anything with these little M's on here, These are mechanisms that you need to learn. These are, of course, the conditions, and this is, of course, the name of the reaction. So AQA people, you've got quite a few mechanisms to kind of look at here, okay? Whereas OCR, fewer is what I'm going to say here, okay? But then, all the exam boards have got their good points and their bad points. It swings and roundabouts here, folks, okay? So download those, okay? Make sure you save them somewhere. Now, just a little pointer here, guys. It's not, is this for OCR-A or OCR-B? This is for OCR-A, okay? Now, I should imagine that it's the same for OCR-B. I haven't done that one, okay? But this is for OCR-A, so if you are doing OCR-B, then just check, okay? So it's going to be useful for you, whatever. So as an example, okay, you've got all these mechanisms. Obviously, I didn't write the mechanisms in here because that would just be like too mental on this sheet. And you know what? It is busy enough as it is. But if you look, one thing I want you to focus on, this goes for year 13s as well. Look at the type of mechanism you've got here. For AQA, it looks like a lot of mechanisms, but those three that I've just highlighted, they're all nucleophilic substitution. So they're all, okay, they're slightly different. You've got a different nucleophile in there, but by and large, the mechanism is exactly the same. So my advice, if you've got a number of mechanisms to learn, whether you're year 12 or year 13, look, you've got electrophilic addition, they're broadly similar. They're not exactly the same, but if you revise mechanisms as these groups, then it is much more palatable and much easier to learn. You can see the comparisons between them. It reduces the kind of load, if you like, in terms of the recall that you need to have. So that's one top tip there for mechanisms, and we're going to be talking about mechanisms later. Now, one last thing I'll mention about these, okay, or two last things. Number one, if you're year 13, yes, this is only half of what you need to know, but I do have a year 13 version, which includes everything, and it includes all the aromatic stuff as well for benzene and the like. So just make sure that you're kind of with me next week. Next week, I'm running these May half-term kind of masterclasses, if you like, or exam training, I'm calling it. So if you want to join that, then there's a link. Well, I'll pop a link in later on for you to subscribe if you want to join me for that. But it is paid next week, okay? So the other thing is, how do we use this? Well, my advice is this. One of these, okay, print one off, all right? Just one. Keep it in your folder. Don't put it on the wall. It's not a poster, all right? And then print a load of these ones off. So these are obviously blank versions of the sheet that we've got here, okay? So I say print loads of them off. The reason being, spaced repetition is the way forward in terms of recall here, okay? And there is a lot of recall. So what I want you to do is use one blank sheet and just dive in. No revising first, okay? Just dive in to find out where you're at. Now, don't try and do the whole thing in one go, okay? Because it's just overwhelming. You're gonna get annoyed with it before you even start. My advice is just stick to one little section, maybe this top triangle here to start with, and try and recall the name of the reaction and the reagents and conditions that you need to have for these reactions. Now, if you do that, check it with this one. If you got anything wrong, this goes in the bin, and you try again, with a little bit of revision, you try again, maybe like the next day, okay? And then once you've nailed it, once you look at it and you mark it, you're like, yeah, I nailed all those, then just try extending the area, okay? Just by a little bit, by 2 or 3 reactions or something like that, and then try that. If you get it wrong, then obviously put it in the bin, you start again or try again the next day, okay? So spaced repetition, and what you'll do is you'll start small, but then all of a sudden you build up to here, then you can build up to here, and then you're doing the whole thing. So you're not just revising this bit, then this bit, then this bit, because when you're doing that, okay, all of a sudden, by the time you get to the end of this, it was weeks ago that you were revising alkanes and alkenes. So just build, okay? So you do 1, then you do 1 and 2, then you do 1, 2, 3, then you do 1, 2, 3, 4. So that's just building your knowledge, and you're just revising and recalling these things all the time. Now, I'll be honest with you, folks, and I'll always be honest with you, it is brutal. It is boring. It is repetitive, and it's nobody's favorite thing to do. But you know what? It works. It works, okay? It is not the most fun thing to do when revising, but it works. So when it comes to spaced repetition, that's where the hard yards are put in. And like I said, it works for these areas in chemistry where you have a lot of recall. to do, okay? But of course, so many other areas in chemistry require you to practice skills and apply skills. Like I said, it's always about what you can do as opposed to what you know. So that's in terms of organic chemistry and how to revise it. That's how I would learn those reactions. And as I say, year 13s, if you're watching this, then in my May half-term exam training, I'm going to be giving out the year 13 versions of those. And it's that AS plus all the A-level ones that you need to know as well. And of course, your benzene one. So, if you are year 13, this is a good place to start because you know what? It is the third most common topic that comes up in A-level papers, and you need to have that kind of knowledge bank in there of your year 12 or your AS, if you like, reactions. Now, any questions on how to go about revising those, about the kind of exam reaction trackers or anything like that, pop them in the chat for me now. Otherwise, we're going to move on to the next thing. We've only got an hour tonight and we've got a lot to cover. I want to give you as much kind of insight and knowledge as I can in terms of to help you revise organic chemistry. So anything you want in the chat, there you go. I'm going to have a sip of this. Okay. So onwards and upwards, ladies and gentlemen. I want to talk to you about isomerism because that comes up a lot in both year 12 exams and year 13 exams, okay? So you need to just have a handle on the different types of isomerism. And I don't know whether you've seen this before, but I know that a lot of students that I teach haven't seen this before in terms of looking at isomerism and just kind of bringing it all together. Because there's no one section in chemistry that says, do isomerism, okay? Learn these types of isomerism and practice these types of isomerism. They're all just kind of scattered around depending on the functional group that you're revising. So this is what I want to do. I'm going to show you kind of how it all kind of links together and the different types of isomerism, okay? So if you want to make notes on this, you are welcome to, okay? So I'm just going to go from first principles here. I'm just going to do chalk and talk, okay? So in terms of isomerism, can't even spell it, Rich. That's not a good start. So in terms of isomerism, there are two major types of isomerism. If you know either of them or both of them, pop them in the chat. I want you guys kind of interacting with this and recalling stuff. So there are two major areas of isomerism that we have. Okay, so first one and second one. Anybody know what those are? You kind of just get involved in the chat and talk to me, folks. I'm going to just give you 10 seconds maybe to pop something in the chat. Let's see if that comes through for me. Two kind of broad areas of isomerism. Structural is one. Thank you very much, Suman. So structural is one. What's the other one? Oh, and fluorine as well. Okay. Thank you very, very much. Stereo. Thank you, Alice. So stereo isomerism. Now, let's deal with this one on the left first. Okay. So structural, there are three kind of subgenres, if you like, of structural isomerism. Now, the first one is chain isomerism. Okay, now chain isomerism, you don't need to know like the definition of it necessarily, but just know that if you are asked to draw a chain isomer, it literally means you need to break the chain and create a side chain somewhere, okay, to make side chain alkyl groups, so methyl group, ethyl group. So if you're asked, okay, so how many chain isomers are there of like pentane, for example? I just take a carbon off the end, draw 4 carbons, and then think, right, where can I put that carbon that I've taken off? Well, the only place I can put it is there, okay? So I can make 2-methyl butane. If I put it there or I put it there, it's the same molecule. We're just looking at it from a different angle. Even if you put it there, it's just butane again. Okay, so you can't just pop it on the other end because you just end up with the same molecule. So 2-methyl butane, and then there's nowhere else you can put that carbon. So shorten the chain down to 3. And now you've got to think, right, where am I going to put those 2? Well, the only 2 places you can put them are there. Okay, so those are your chain isomers, and that's how we deal with those types of questions. I don't like it in exams. They very often kind of like just treat these things the same, even though they're not. So structural isomers are the overarching type of isomers that we're talking about here. So we've got chain isomers. We've also got positional isomers. And let's just stick to capital letters, Rich. Position. Now, positional, nice and easy. I'm just going to do it kind of vertical here. A positional isomer is referring to where on the carbon chain is your functional group. Okay, that's a positional isomer. You are just changing the position of the functional group. Now that could be an alkene, so butanene or butene. It could be 1-chlorobutane or it could be 2-chlorobutane. So you're literally just moving them up and down the chain. That's a positional isomer, so watch out for those. So they don't change the chemical properties or indeed really the physical properties of your isomer, because they're essentially got the same functional group. Okay, same functional group. So all it is just moving like an OH or a chlorine or a ketone group maybe in the middle of the chain. So yeah, just moving it up and down the chain. You're not breaking the chain. Anybody know the third type of structural isomer that we've got here? I'll just give you 10 seconds to do that. What is the third type of structural isomer that we can have, folks? Any takers? Yes, it is, Alice. Fantastic. So functional group isomers. Now, functional group isomers do exactly what they say on the tin. That's an old phrase. They come in pairs, all right? And it's good to have a list in your mind about what those pairs are, okay? Because they change, of course, because you're swapping. It's the same molecular formula, but obviously you're rearranging the atoms in there to create a different functional group. And with a different functional group, of course, you end up with a whole different set of chemical properties. Now, the first one, I would say, is alkene and cyclical alkane. Okay, so for example, you could have butene, okay, which is C4H8, but equally you can have C4H8 in a cyclical fashion. These are all hydrogens, of course. Okay, so they have the same molecular formula, but a different functional group. Technically, alkane isn't a functional group, is it? But you see what I'm saying. Okay, decolorizes bromine water, does not decolorize bromine water. Okay, so you do end up with different chemical properties. Another pairing, which is pretty common, is aldehydes and ketones. Okay, now some of you need to worry about those at AS or Year 12, and some of you don't, but I'm just covering all the bases here. Aldehydes and ketones are one. Essentially, an aldehyde, if we do this, I mean, it's just a ketone group on the end of a molecule, isn't it? But they do have different chemical properties, and that's why they're classed as different functional groups. Another one, carboxylic acids and esters. Okay, again, same molecular formula, different functional groups. So they both contain 2 oxygens. So you've got your carboxylic acid like so, but equally in an ester group, you have this ester group in the middle of 2 carbon chains like so. So carboxylic acids and esters are another, set of functional group isomers. Now, they are the main ones. Okay? Year 13, just a little kind of mention of acyl chlorides and basically like multiple functional groups. I suppose an acyl chloride, you could actually have a functional group isomer of an acyl chloride as maybe like a ketone and just a haloalkane, I suppose. But that's a really weird one. I just thought I'd mention it. So those are your 3 types of structural isomers, guys. And when they ask you questions in the exam, like, draw a blah isomer of this, then just watch out for those 3, okay? And like I said, they can just kind of do this and say structural isomers. At that point, I would imagine you're well within your rights to do any of these things. So just be aware of the wording in the question and know what you're allowed to do in order to answer the question. So, bit simpler for stereoisomerism, okay? One is AS and the other is A level. The one in AS, which you guys need to know, is, of course, EZ isomerism, okay? So, Entgegen and Zusammen, there are 2 things that you need in order for EZ isomerism to appear in a molecule, or for that molecule to show EZ isomerism. Just a word of warning now, not a word of warning, but just an update really. Stereoisomerism is all about how molecules, the groups in a molecule, occupy different relative positions in space. So to the untrained eye, they look like the same molecule, but they're actually not. Okay, so the groups occupy different relative positions in space. So what are these two things that a molecule must have in order to show EZ isomerism? Well, the first one is a C double bond C. Okay, now normal single bonds rotate. These do not. These are non-rotational. That is a beautiful word to put in if you ever get asked, why does this molecule show EZ isomerism? A, it's got a C double bond C, which means that it's non-rotational about those two carbons, because it means that if you got X, Y, and W and Z, that can't spin around. Okay, so that means this Y relative to this W is in a fixed position. They are different relative positions in space. The only way in which you could kind of get this Y down here to a different relative position is break a bond and make a new one. Okay, that's what you have to do. And then it becomes a different molecule, of course, doesn't it? So the first thing is C double bond C. And then the other thing, and this is always kind of hard to word, I found with students in the exam, is that each carbon on, or in, I should say, in the C double bond C must be bonded to two, and this is the key word, different groups. Now, it doesn't matter what those groups are, okay? They can be methyl groups, ethyl groups, propyl groups, whatever. It could be like an OH, a chlorine, just a hydrogen, like literally anything, okay? So you've got to be able to spot. They just have to be different to each other. So let's say this, I use W and X here. They just need to be different to each other. They just need to be different to each other. They can be mirrored over here, and that's absolutely fine, okay? But essentially, as long as these two are different from each other and these two are different from each other, it doesn't matter that they're the same and they're the same, okay? They just need to have two pairs on either side, left and right, that are different to each other. So just watch out for these, okay, guys? Because the classic question is like, oh, we've had an elimination reaction. Little point here, guys. If you are making an alkene from anything, it's an elimination reaction. Or if they tell you this happens in an elimination reaction, you will be making an alkene, okay? Elimination reactions and alkenes go hand in hand. Now, the classic question is, this elimination reaction occurred and it made 3 different products. Now, very often, 2 of them are different products. Maybe the alkene, the C double bond C, formed in different places on a carbon chain, okay? And that's absolutely fine. But then you can't think of the third one. The third one, because of the C double bond C, one of those first 2 products is going to have a Z isomer and an E isomer, and they will be your 3, okay? So isomers count as different products, of course, right? So just watch out for these. Other questions that might come up, which do come up, okay, are obviously in a larger molecule, like how many EZ isomers can occur out of this, okay? If they've got more than one C double bond C, you can have multiple E and Z isomers. The other thing to watch out for is if they ask you how you prioritize, okay? So check your specs. I know it's in the AQA and OCR, I think, where you need to kind of regurgitate the whole Kahn-Ingold pre-log system of how you decide which is the priority group, okay? So for me, in terms of priority groups, most of the time in questions, you just need to make a snap decision. Is this E or Z? So let's just call this CH3. I'm just going to put hydrogen there. I'm going to put chlorine there and a bromine there. And you need to decide, is this an E or Z isomer? Now, unofficially, if you just need to decide whether it's E or Z, just look for the groups that have the largest mass, okay? So which has the largest mass out of these 2, and which has the largest mass out of these 2, whether it's an AR if it's an atom or an MR if it's a group, all right? Now, that's not the official explanation of how you decide which is priority, but it just makes life easier when you're in an exam. So here the CH3 is clearly heavier than a hydrogen, and the bromine is heavier than the chlorine because it's got a greater AR. Okay, so those would be our functional groups. Now, of course, the last thing we need to decide, is this E or is this Z? Well, if you need to go through the middle of that C double bond C to get from one priority group to the other, that is an E isomer, okay? Entgegen, I think, means opposite. My German's not up to scratch, but I think that means opposite. But the one I always remember is if we draw this molecule out again, CH3, hydrogen, but this time the bromines at the top, because they are on the same side, it's the Z isomer, okay? Because they're on the same side, it's the Z isomer, okay? So, as I say, these will feature 100%, I think, in your end of year exams, year 12 people, but they do tend to crop up pretty often in your A-level exams as well. So just make sure you're up to scratch on that, okay? So that's E and Z isomers, obviously in a real nutshell here. We are revising, okay? We got a couple of other things that I want to cover in terms of organic chemistry to make you aware of the most common questions and exam technique. Now, the other type of stereoisomer, year 13s, you'll know about this. Year 12s, you won't know about this. So I'm not going to spend too much time on it. It's optical isomers, okay? Now, optical isomers for year 13s, just very quickly, keywords all over the place here, okay? You've got the word chiral, okay? You've got the word enantiomer, okay? Racemic mixture. All those keywords you need to know the meanings of and be able to use in a logical way in your answers, okay? So for optical isomers to occur, we need a chiral center. What is a chiral center? Well, that is a carbon, and it's always tetrahedral around a carbon in an organic molecule, of course, if you've got 4 single bonds. So it has to have 4 single bonds for a kickoff. So if you see a carbon with a double bond, it's not chiral. Never, okay? But you need to have W, X, Y, Z, 4 different groups bonded around that carbon, okay? So essentially, you're just looking for any groups. Hydrogens, chlorine, CH3, C2H5, methyl, ethyl, propyl, butyl groups, okay? Sometimes they're part of massive molecules, like massive skeletal molecules. All you're doing is just looking for like the rest of the molecule on one side, okay? So a group, it doesn't mean like just an individual tiny little group. It could be the rest of a huge molecule that's bonded, just happens to be there. So you're just looking for 4 different groups, and that is your chiral center, and therefore it will have optical isomers, okay? And of course, the isomer of this, the optical isomer or enantiomer of this, is if you draw a line down here and you flip it over, it's the mirror image, okay? So you've probably seen this example, okay? Your hands, okay, are optical isomers of each other. They are identical in every way. It's just they are not superimposable on each other, okay? So you can't actually do that. So they're not superimposable on each other. They are mirror images, okay? So that is then a perfect example of what optical isomerism is. Ibrahim, thank you for your question. So for OCR, usually last year in the AS paper, there was something about priority system and said the same side and mentioning the groups instead of the MR and AR. Is this common? It's not common. It's what I was talking about, Ibrahim, in that it is the Kahn-Ingold pre-log system. Let me just write that down for you. So just so you know, Kahn-Ingold pre-log system. And it revolves around atomic number, not AR. Okay, so it revolves around atomic number. So you go to the atomic number of the atom that's bonded to the C double bond C. So you've got a carbon here versus hydrogen. Okay, now of course the atomic number of carbon is 6. This is 1. So carbon wins. That's why it's priority. Same here for chlorine and bromine. Okay, they've got obviously bromine's got a larger or higher atomic number than chlorine. However, very, very quickly, if you have got a CH3, for example, here, and a CH2CH3 down here, the Kahn-Ingold pre-log system says, well, okay, you look at the atomic number of the atom bonded to that carbon in the double bond. Well, that's atomic number 6. That's also atomic number 6. Okay, what do we do then? Right, well, we move to the next atom in the chain. Now, it doesn't matter which of these it is, but the next atom in the chain here clearly is hydrogen. The next atom in the chain here that has the next highest atomic number is carbon, okay? So this is the difference between these two. You just go to the next one in the chain. So that's why, officially, why that would be priority over a CH3, okay? But like I said, if you're not asked to explain specifically the system for deciding which is a priority group, then you can just use like, or whichever's the biggest, you know, like whichever's the heaviest, okay? That'll be your kind of little cheat way of doing it. If you just needed to decide on the spot whether it was E or Z, okay? But do check up on that Carn-Ingold system because, as I say, especially for AQA, I think it's AQA, OCR, and Edexcel. You all need to kind of get a grip on that. Excuse me, I went down the wrong way. Typical. Can't talk and drink at the same time. Okay. Excuse me. Right. Don't worry, I'm okay, guys. So, learning reactions, know your isomerism, because isomerism questions, I'll be back to normal in a minute. Isomerism questions are going to be in your paper. So like I said, just be aware of this kind of overview of isomerism and know what you're looking for in those different types of molecules when you're asked questions about it. And like I said, watch out for those questions where, 3 products are made in a reaction. 2 of them may be positional, and 1 of them may be optical or EZ or something like that. So just watch out for those. Getting back to normal now. Okay. Mechanisms, guys. I make no apologies for getting on a bit of a soapbox about mechanisms. Now, a lot of the time, and students come to me all the time talking to me about like, what's the best way to learn mechanisms? And I say, don't learn them, okay? And that just sounds mental, I know, okay? I don't really mean that, okay? But spend less time trying to learn parrot fashion a mechanism and spend a bit more time asking yourself, why? Why does that happen, okay? Why does this mechanism show what happens to this molecule? Because more and more, especially over the last 2-3 years, all of the exam boards, it's like they all got their heads together. All of the exam boards have started questioning you on mechanisms using mechanisms that you've never seen before, okay? Because the exam boards are probably cottoned on. Students are just learning them. Students are just learning. They have no idea why that curly arrow goes from there to there, or why there's a delta positive and a delta negative on this, or why there's a lone pair on that. And that's what they want to examine you on. They want to test you on your skills in chemistry and your understanding in chemistry. And of course, just remembering a sequence of arrows and pluses and minuses, that doesn't make you a good chemist. So they're changing the way in which they examine you, okay? Don't trust me, I've done every single exam and I've seen the difference, okay? I've been tracking these. So understanding mechanisms is by far and away the most effective way of doing this, okay? Because if you can, if you're regurgitating and all of a sudden you forget, you're like, did that arrow go from the hydrogen to the double bond or the double bond to the hydrogen? I can't remember. You've got no basis to work out what the correct one is, okay? So understanding mechanisms is hugely important, not just from a fundamental perspective of being able to remember them, and it helps you remember them, but also, like I said, the exams are changing or have changed, and now they're testing your ability to kind of think on your feet with mechanisms rather than just regurgitating stuff, okay? So let me give you it'll be less than 10 minutes, okay? I'm going to give you just a few little insights as to how to understand what's going on with mechanisms. Now, I appreciate that some of you, I might be preaching to converted already, all right? Some of you might have great chemistry teachers who have taught you this rather than just going, there's the mechanism, learn it. Okay, so let's have a look at one that we all know and love, and probably one of the first ones that you learned, and that is nucleophilic substitution. Okay, so we start with a haloalkane. Now, the first thing is, the one that you probably learned was something like this. okay? And you're just using chloromethane or something similar. Of course, in an exam, are they going to give you chloromethane? No, okay? Like you learned free radical substitution, that series of reactions, initiation, propagation, termination. You probably did it for methane. Are they going to give you methane in the exam? Of course they're not going to give you methane in the exam. So, you need to kind of work a little bit outside your comfort zone. So, what's going on here? Well, first and foremost, you get marks. I'm going to do this in purple on the left-hand side here. No, right at the top. You get marks for curly arrows, charges, okay, or kind of partial charges, using the use of lone pairs, and of course the use of full charges as well. That is what they are looking for, and they are looking for you to be really accurate with the positioning of these things. And again, understanding how and why they've got these things, that goes a long way to helping you remember these mechanisms. Now, very importantly, what does a curly arrow show? It shows the movement of a pair of electrons. A pair of electrons. Not just electrons, not one electron, but a pair of electrons. Okay, that's really, really important. So what this tells me is, and you can write this down if you want, it's easy to remember, electrons always move from where there's more of them to where there's fewer of them. Okay, that's just logical. If you're drawing a curly arrow, well, it shows the movement of a pair of electrons. Well, it's got to come from where the pair of electrons comes from, going to somewhere where there are fewer electrons. Okay, because they're negative, they're going to be attracted to something delta positive or positive. Okay, so from where there's more electrons to where there's fewer electrons. Ask yourself, if you ever get in that situation, it's like, oh, which way does a curly arrow go? Right, where's the most electrons? Right there, okay? So it comes from there to the other place. The other thing I will say about these, in fact, let me just move this down a little bit because I'm going to run out of room. The other thing that I'll say about these is you are always either making or breaking a bond. So whenever you put a curly arrow in, be sure, okay, you're either making a bond or you're breaking a bond. Every single time in organic mechanisms with curly arrows, you are employing heterolytic fission, okay? Heterolytic fission. So anytime a bond breaks, it's heterolytic fission, apart from initiation step in free radical substitution. That's the only time you'll come across homolytic fission, or those of you who need to do ozone as well, maybe there's a touch of it there. But by and large, all the mechanisms, the curly arrow mechanisms that you're drawing, because free radical substitution isn't one of those, it's just a series of reactions. It shows heterolytic fission every single time. You're making a bond or you're breaking a bond, okay? And that means, your curly arrow is either going to come from a lone pair on something, okay? So that lone pair goes to make a bond with another atom, or you're coming from a bond to an atom, okay, whereby that bond is breaking, all right? So that's the only two times that you're using a curly arrow, is you're making a bond using a lone pair on something, or you're breaking a bond using that electron pair in the bond, okay? So first and foremost, we need to think about what drives organic mechanisms. Well, what drives everything in chemistry? And that's the attraction between something positive and something negative. Electrostatic attractions, okay? Now, alkanes, okay, so boring old alkanes, they're non-polar. That's why they're so unreactive to nucleophiles and electrophiles and things. That's why we need crazy free radicals to attack them, to actually do any kind of damage, if you like, and cause them to undergo a reaction. So it's dipoles that basically make the organic chemistry world go round. All right, so you're always on the lookout for dipoles. What does that come back to? Difference in electronegativity. Okay, how do we know there's a difference in electronegativity? Well, if you've got a bond between two atoms that are different, there's going to be a polar bond there. There's going to be a difference in electronegativity. What drives electronegativity? Atomic structure. Don't get me started on that. Atomic structure, and knowing your atomic structure again helps you understand why you get so many of the trends and stuff that we do in chemistry. But maybe that's for another time. Okay. So, spot the dipole first and foremost. Chlorine, more electronegative than carbon. So we've got delta plus and delta minus, okay? Remind me in the chat. It's the same for everybody. It doesn't matter what exam board you are. What reagent do we need in order for nucleophilic substitution of this haloalkane to produce an alcohol? Oops. Put it in the chat for me, guys. Be specific about your reagent that you need for this conversion here. Be specific for me. Pop it in the chat. What reagent do you need to convert a haloalkane to an alcohol? Suman, half marks. Potassium hydroxide? Yes, it is. Okay, so it's the hydroxide that we need in order for this reaction to be fluorine. Again, half marks. Okay, let me just go back to this. Let's go to the AQA one because it's the same for everybody. Look at this. Okay. So I'll just highlight this. Aqueous potassium hydroxide gives you an alcohol. If you use alcoholic potassium hydroxide, so let's say potassium hydroxide dissolved in ethanol, then you get elimination and you end up with an alkene. So if you're asked what the reagent is for nucleophilic substitution, then it's aqueous sodium hydroxide or potassium hydroxide, doesn't matter. It can be lithium hydroxide. You know, it's the hydroxide that's the important bit. But it's aqueous gives you alcohol, but alcoholic gives you alkene. Okay, so it's kind of a bit counter. It'd be nice if alcoholic gave you the alcohol. That's just not the way it is, sadly. Okay, so aqueous gives you the alcohol, alcoholic gives you elimination and the alkene, folks. Okay, it's a very important difference, and they like to put it in the exams because not many students remember it. But that's why I'm here, is to give you the insights to make sure you learn the right things for your exams. So it's curly arrow time, folks. Notice how our nucleophile here does have a lone pair. Every single nucleophile that you come across will have a lone pair. Not all of them have negative charges, but all of them have a lone pair, okay? So ask yourself, what does our curly arrow show? It shows making a bond or breaking a bond. They've got to go from where there's more electrons to where there's fewer electrons. Well, this is going to attack our delta positive carbon. Opposites attract. So make sure, especially OCR people, because they go out of their way to draw a billion different diagrams in the mark scheme to say what they accept and what they don't accept. And you need to be very careful about the positioning, everybody does really, of your curly arrows. Remember, it goes from a lone pair to the delta positive carbon. In this respect, I am making a bond, okay? Because that's what needs to happen in order for that alcohol to be on there. But of course, at this point, we now have technically 5 bonds around that central carbon, and we all know that carbon can only form 4. So what has to happen as a consequence? This is a consequential curly arrow now, because this bond is formed. Now this bond is going to break. It has to break. Now the question is, why is it this bond? Why is it not just that one? Okay. The point here is that this is a very polar bond. Okay. Now, I'm going to use a different color. That means that this pair of electrons in this bond spend most of their time with chlorine. Now, if that pair of electrons, even though one of them belong to carbon, if that pair of electrons spends most of its time with chlorine, it's a really polar bond. And in fact, the more polar a bond is, the weaker it is, and therefore the more likely it is to break. That's a good thing to remember as well. Okay, so the more polar a bond, the more likely it is to break. Okay, so that's why this bond does break. And this is where this comes in. Oops. So this pair of electrons here, I'm using a different color to see it show the 2 stages. They both move to this chlorine atom. Okay, and that means that bond is now breaking. And of course, it's a one-stop shop. We end up with our alcohol. And lastly, of course, we must always show what else we produce. And that is, in this case, a Cl- with a lone pair in it, this pair. Okay, I know I've drawn 2 dots there, but that doesn't matter. It's still a pair of electrons, right? So that's what we're making. So my point here, folks, is that in any mechanism you learn, okay, and let's just reference the AS ones for now, okay, whether it's electrophilic addition, whether it's nucleophilic substitution or elimination, okay, ask yourself when you're learning these, first of all, as I mentioned before, group them, excuse me, so learn all your nucleophilic substitution ones together, excuse me, and then secondly, when you're learning them, always ask yourself, right, why does that bond go from there to there? Because if you just parrot fashion learn them and you forget in the exam which way the arrow goes, you've got zero backup, like zero backup. So understanding them, massively, massively important, guys, okay? And I'm going to be going into more detail about this in terms of the year 13 mechanisms things next week in my May half-term exam training, okay? So make sure that if you're year 13, if you want to join me, there are still spaces on that. I'll post a link actually in a minute, and you guys can check it out if you like. Okay. In fact, let's just post that link in here now, just because we can. Okay. So this is May half. Can't spell term exam training. So in that link there, don't worry, you're not just going to get registered if you click that. It takes you to a page where you can read a bit more about what I'm doing, why I'm doing it, and how it helps. Okay, I've been doing this for 20 years now, folks, so I know what I'm doing, and I've helped loads of I've helped students go up 2 grades in about a month, using kind of what I'll be doing next week. Okay, so if you're interested in that, then do come along. Okay. And it works out at like less than $10 an hour. So it's, you know, I like to think I'm kind of sharing the love a little bit with everybody as well. Don't choke, Rich. Don't choke. So last thing on these before we move into the final section. Now, this here is, it's something for you all to have a go at. But if you're year 12, I don't really want you to worry too much about this. Okay, this link here, this is for organic mechanisms that are unknown, okay? So that PDF basically gives you some questions from an AQA exam. There's another AQA one. There's an OCR one, okay? There's an Edexcel one, okay? They're all at it. These are examples of mechanisms that basically you don't know. They're basically not in the spec, okay? So, for example, this one here, say it's an incomplete nucleophilic addition. Now, I know this isn't year 12, but I just want to show you that, you know, they've given you the first part, okay? You don't need to know the mechanism for this, but it's about a game of spot the difference. What bond has formed? You can see this here, that bond is broken. Where's that lone pair got? Where's that pair of electrons gone now? Well, they are here, so that means that's fully negative. This has formed here. Okay, so that's why we've got that bond there. And then it's again, spot the difference again. What must have happened to that hydrogen? That hydrogen must have broken off. There it is up there. Okay, so that hydrogen, that pair of electrons must have broken that bond there. But of course, that's the wrong way. Why is that the wrong way? Well, because we've got a H plus there. That wouldn't be a H plus if it had 2 electrons around it now, would it? Okay, so what we need to do is make sure that that arrow goes to this oxygen, okay, to resatisfy it, because we know this oxygen has always got 2 lone pairs on it, okay, because oxygen just does when you find it in organic molecules, okay. So this is why I'm telling you this. It's a lesson for all of you, okay, but I think maybe a bit more for the year 13s in the respect that, you know, you find these a bit more in year 13, but year 12s, like I said before, understanding your mechanisms and why they work and how they work is just A, hugely important if you're going to smash your A-level exams, but B, at the very least, it's going to help you if you kind of come unstuck when actually kind of drawing a mechanism in an exam and you're kind of like, oh, which way does that curly arrow go? I can't remember. Okay, so mechanisms, understand them, don't just parrot fashion, learn them. Okay. Do I have the mark scheme for this? That is a very good question. I'll see at the end if I can find it, okay? Where can I find the mark scheme? That is a very good point. I thought, to be fair, that it was on the end of that, and I've just discovered that it's not. So I tell you what, let's just have a quick look. If you bear with me just 60 seconds, guys, I should be able to find it. Just talk amongst yourselves. That's absolutely fine. No, I haven't actually put the mark scheme on the end of that, guys. I do apologize. No, I haven't got it. Sorry, guys. But you know what? It just serves as a bit of a kind of reminder, really. Just kind of take a look at them, see what I'm talking about. So apologies for that. I thought I had it, but I don't. Okay, and I can't build it right now because obviously you guys are watching and you want stuff. Okay, you want advice. So where are we at so far? Number one, reaction trackers. Okay, use those, abuse those. Spaced repetition. It's hard work, but it's good work. Okay. Secondly, obviously, in terms of your isomerism, make sure you're up to speed with those, and organic mechanisms and those unknowns as well. Okay, folks, so just be prepared for those where you can. Now, lastly, there's one I wanted to touch on: calculations. Okay, because in organic chemistry, we think, we tend to treat that completely separately to a lot of the calculation side of things that we do. Because, of course, we think calculations, we think titrations, we think physical chemistry, essentially. That's where we think all of our calculations are. Not true, okay? Anybody know? I'm just going to open this and see if anybody's kind of realized this. What is the most common type of calculation that's associated with organic chemistry, do you think? And I'll give you a clue. It's like the practical side of things. What's the most common type of calculation you think crops up with organic chemistry? And I'll just leave you just for a few seconds to kind of think about that. And pop it in the chat for me. Any takers? Just a hazard a guess. Because this is what I'm good at. I've analysed all the papers. I know what's what. I know how often things come up. All right. Enthalpy, mole calculations, enthalpy. Interesting enthalpies come up a couple of times there. Bond enthalpies, yeah. Rate equations, titrations. No, it's none of those. Okay. Interesting about enthalpy though. Yeah, I mean, I suppose they do tend to give you like the calculate enthalpy of combustion if something's burning, and they ask you to find the delta H for that, and it's usually an organic one. Yeah, so I'll probably give you that. Boom, Seth, top prize. If I had a prize, I'd give it to you. If I got a prize, I don't have a prize, but top prize for you, mate. Yes, 100%. It is no pun intended. Percentage yield. Okay, percentage yield calculations always crop up where organic chemistry is sniffing around. Okay, so let me just show you. I have got this for you, and there is a mark scheme attached to the end of it. I apologize about the last one, guys. But what we've got here is a collection of percentage yield calculations that are all linked, well, vast majority linked to organic chemistry. So these are all questions that you guys can do working with percentage yield and, look, organic chemistry percentage yield, the importance of percentage yield and atom economy when producing molecules, again, percentage yield and so on and so forth, okay? So you'll get questions like this: calculate the percentage yield. Now, I know we all know what the equation for percentage yield is, because percentage yield equals your actual divided by theoretical times by 100. Okay, that's what that is. Okay, and you know, to be fair, like in this question here, they're asking you to calculate the percentage yield, and that's absolutely fine. That's nice and straightforward. Little word to the wise though, guys, this can be mass or it can be number of moles. Okay, usually you end up with one of each, and it's really annoying. Okay, so you got your actual mass, and then you calculate a number of moles that's theoretical. Okay, so if it was 100% yield kind of thing, it doesn't matter what you do, whether you convert this mass into a number of moles and then do it, or you can convert the number of moles into a mass and do it. Just whatever works for you. Okay, you're going to get the same answer. Okay, so whether you're using actual masses, the mass of your product, the actual mass of your product and the theoretical mass, or the actual number of moles and the theoretical number of moles. And like I said, annoyingly, you usually end up with one of one and one of the other. Doesn't matter which way around you do it, okay? The tricky bit comes in, and this is where students lose most of their marks with percentage yield calculations, is when they're not asking you to calculate the percentage yield. It's when they ask you, well, it's a 32% yield, how much kind of reactant do we need to produce this mass of product, for example? Okay, let me see if I can find one in here for you. That's calculated percentage yield. That's calculated percentage yield. There we go. Okay, oh no, that's not one. Okay, there we go. Let's go through this question, okay? Have we got time? Oh, not really, but we'll do it anyway, okay? Because you guys are here and I'm here, and let's do it. So, you got a one-to-one reaction here. You're going from hexane 1-ol to hex 1-ene. So, an expected percentage yield of the product is 62.5%. A student plans to prepare 4.2 grams of hex 1-ene by this method. Calculate the mass of hex 1-ol that the student should use and explain how you should obtain pure hex 1-ene from the mixture. Okay, so that's a big old question here, but we're just dealing with the first part of it. So we want 4.2 grams. The percentage yield is 62.5. Now, obviously, we can't just stick with mass here because we're using stoichiometry. We need a number of moles in order to use stoichiometry. Okay, so the first thing to do is find the number of moles in 4.20 grams. Okay, now I'm not going to do that right now because I haven't got the MR off the top of my head. Is it in there? No. So let's just say, I don't know, that it's, 9.1 moles. Let's just go 9.1 moles. I'm just making that number up here because this isn't the important part of the thing. Okay. So let's say that we want 9.1 moles of this. Now this is a 62.5% yield. Okay. That means that if I put 100 moles of alcohol in, I'm only going to get 62.5 moles of product out. That's what that means. So what you need to figure out is 9.1 is 62.5% of what? Okay, 9.1 is 62.5% of what? And that's how we work backwards here, okay? So to do that, I do 9.1 divided by 62.5, okay? And I'm going to do that on my calculator, times 100, okay? So what we're doing here in this first bit is finding out, well, what's 1%? Okay, so if I divide 9.1 by 6, and 9.1 represents 62.5% of the number of moles of this, if I find 1% by dividing 9.1 by 62.5, and then multiply by 100 to get 100%, okay, that's technically our theoretical yield, isn't it? The 100%. And that gives us 14.56 moles. Okay, now I'm just using random numbers here, but that's our answer. That's how many moles of alcohol we need to put in. And then, of course, you turn that into a mass. Okay, and that's nice and easy, you know, because it's literally just number of moles times MR. So when you get these questions where you're asked to essentially rearrange this expression, okay, don't think of it like a rearrangement. Okay, think of it like, okay, this represents 62.5% of what? Okay, convert it into a number of moles. then find the, if that's 62.5%, what's 100%? And that's what you need to do here, okay? So that's essentially percentage yield, guys. And usually I'd say 99% of the time when you're working with organic chemistry and percentage yields, you are looking at a one-to-one reaction, and you don't need to worry about that. I don't think they're going to give you any 2-to-1 reactions. That just muddies the water in terms of percentage yield and so on and so forth. You can see this is 1-to-1 here. You can see that, this reaction here is, 1-to-1. Any reaction 1-to-1. So you don't need to worry about the stoichiometry in that respect. Now, as I say, I promise that there are answers to this at the end of the worksheet, guys. Okay, so this is percentage yield, and you are welcome. Okay, so organic chemistry. Let's just kind of come back to me for a sec. So organic chemistry is huge. It's like learning a new language, okay? So my advice is, obviously we're on the kind of cusp of year 13 exams, year 12, you're not so far away with your internals either. But obviously give it some time. That is the most time-consuming bit of chemistry. The rest of it, okay, is just work, practice, questions, okay? Now you've got those questions to practice percentage yield. If you can do those, you can do any percentage yield question that they throw at you, okay? A lot of students think, I just need more questions. I need to do as many questions as possible. No. What I do is I kind of distill those down, okay, to the different types of question that are going to come up, okay, or may come up, of course. So I don't know whether, if you see my TikToks, year 13s, I talk about the 3 types of buffer calculation that you can ever come across. There's only 3, and if you can compartmentalize, then all of a sudden they're just super easy, okay? Same with Hess's law questions for year 12. That's exactly, and a little bit of an advert here, is what I'm doing tomorrow at 6 o'clock. So I'm looking at enthalpy, I'm looking at calorimetry, I'm looking at Hess's law, and I'll be giving you just the 2 types. There's type 1, and then there's type 2, and then there's in brackets type 3. Okay, and I'll show you those. Type 3 suck, but they're rare, so that's okay. So I'll be going through those tomorrow. And again, that is the second most common topic that comes up in A-level exams. But of course, you AS students, it is here for you to learn as well in readiness for your end-of-year exams, which is super important, of course, because that pretty much dictates what your predicted grades are going to be, which is then going to dictate which unis you can apply to and so on and so forth, and which courses. So, mark out of 10 for usefulness today, guys. Just give me a little score on the end there. I don't mind, okay? Be brutal if you like. I'm a big boy, I can take it. Like I said, I just wanted to kind of put this out there to let people know what I'm doing and letting people know exactly what I'm doing to help over the next few weeks. Year 13s, okay? Join me for exam training, okay? It's about what you can do. I'm going to be giving you cheats, hacks, tips, tricks, all right? Just all the good stuff, all killer, no filler, next week. If you want to register, then all you have to do is just click this link, okay? And you will be taken to a page, and yes, it costs cash money, okay? I mean, this is just what I do for a living. I've tried to put as much as I can out there into the ether just to kind of just good karma, but equally, them's the breaks, isn't it? Okay, so, and it works out less than £10 an hour. And what I'm going to be doing is I'm going to be not only providing you with 10 hours of tutoring next week, but I'm going to be inviting you to join me live the night before each exam. So I'm going to be coaching you right the way through your exams, okay? And it's just one-off thing that you have to pay, and then that's it, okay? So thank you very much for those, guys. 8.9, very specific. Ibrahim, I like that. Be accurate, okay? I didn't specify that I needed 2 significant figures, but well done you for doing that. Thank you very much. All right, so thank you very much, guys. I really appreciate that, and I hope to see you here for enthalpy tomorrow. And if you got any mates or classmates or whatever that you think this would be helpful for, then just ping them a link to my YouTube, ping them a link to my TikTok, and they can come and watch the recording, and they can join me live tomorrow, join us live tomorrow and Thursday as well, if you like. They are recorded, Suman, and you know what? I'm going to keep these up for the rest of this academic year. So basically come the end of June, I'll probably take these down because next year I'll be kind of running new ones and different ones and so on and so forth. You know, we live in the here and now, right? So, so yeah, I'll leave these up for the next few weeks. They'll automatically just stay on my YouTube channel, and you know, keep an eye on my TikTok as well because I'm always doing stuff on there and kind of putting little updates and little tips and tricks and hacks and stuff like that. Okay, and yeah, if you guys need any help, you know where I am at chemistrycoach.co.uk, and that's where you can find the links to the May half-term exam training for year 13s as well. Okay, so thank you so much for coming along today, guys, and getting involved and asking questions. I love it. Okay, there's nothing worse than when no one's talking to me, and hopefully I will see you tomorrow, same time, same place at 6 o'clock. We'll be going through enthalpy, and then Thursday, the most common topic that comes up in A-level exams from year 12 is bonding. And I promise you that is gold. That is bonding is probably one of the worst taught parts of A-level chemistry. It drives me insane, but I'm here to simplify it for you, and you can hack any bonding question just by using these simple tips I'm going to be giving you on Thursday. Okay, so make sure you come along to that, and I will catch you over the next couple of days. Cheers, guys.